Good morning, everyone. Welcome back. I hope that you all had a great long weekend and that you're doing fine today. We're looking at lesson 30.08 today, which deals with what we call total internal reflection. And this lesson can be found on page 2 of your new lesson handout, which is Physics 30, the rest of the story, part 2. So we're going to start with a warm-up. In fact, pretty much the whole lesson is the warm-up. What we've got is light traveling from a container of water into air. So it's going from the water, and you're given the index of refraction of the light in the water. I just want to add it to our diagram. You're given the fact that N in the water is 1.33. It travels into the air. You should know that N in air is 1.00. And the first thing we are asked to do is to sketch the refracted beam of light. One of the things you should have learned from the last lesson is that when you have light that travels from a more dense medium like water into a less dense medium, that it refracts away from the normal. Now, I don't know exactly how far away from the normal it's going to refract in terms of an angle, but we do know it will refract away from the normal. And what that means, everybody, is that theta 2 is bigger than theta 1. The angle of refraction is greater than the angle of incidence. Now we're asked to do a few calculations. We're asked, well, if the angle of incidence is 15 degrees, what's the angle of refraction? And what's the angle of refraction if the angle of incidence is 25 degrees and 35 and 45, etc.? So let's write out what Snell's law has to say about this. It would be sine of theta 1 over sine of theta 2 equals N2 over N1. If I cross multiply, I get N1 sine theta 1 equals N2 sine theta 2, which means that sine of theta 2 is equal to N1 sine of theta 1 over N2. And we can go even further with that. Since N2 is 1.00, go back here. I don't think I labeled it, but since the light goes from water to air, the 1.33 is N1 and the 1.00 is N2. It's the second index of refraction. So since N2 is 1.00, that means that sine of theta 2 is equal to N1 multiplied by sine of theta 1. So to calculate all of these theta 2's is really kind of trivial in terms of complexity. All we have to do is take 1.33 times sine of the angle of incidence and then take the inverse sine. Okay, well, here we go. I'm going to take the inverse sine of 1.33 sine of 15. I'd better make sure that I am in degree mode, and I am. You could, if you wanted to, take 1.33 times sine 15 and then take the inverse sine. I'm just choosing to do it in one shot. We get 20.1 degrees. If I do the same thing at 25 degrees, I'll just do these in batches. I get 34.2, so 20.1 and 34.2. You'll notice that the angles of refraction are indeed bigger than the angles of incidence, which means it refracts away from the normal. Continuing on, we'll do the 35 and the 45. At 35, we get about 49.7, and at 45, we get 70.1. So 49.7 and 70.1. And now we're going to do it for 55 degrees. and we get an error. And it isn't that I've entered anything wrong. The reason I can't get an answer is that 1.33 sine of 55 gives me a number larger than 1. So what I'm saying here for that 55-degree angle of incidence is that the sine of the angle of refraction that I'm trying to solve for is equal to 1.0, I think I saw 0.8 there, it doesn't matter. It's bigger than 1, and the sine of an angle cannot be bigger than 1. There's all kinds of reasons why we know this. If you look at a right triangle, sine is opposite over hypotenuse. The only way the sine of an angle can be bigger than 1 is if the opposite side is bigger than the hypotenuse. But the hypotenuse is the biggest side in a right triangle. So this is impossible, which means you get an error here. There is no theta 2. The light does not refract. So what does it do instead? When you are unable to calculate an angle of refraction, refraction does not occur. Instead, all of the light will reflect off of the boundary and back into the first medium. This is what we call total internal reflection. Now I'm going to show you a demonstration in a minute or two showing light refracting from water into air. And even when the light does refract into the air, some of the light will always reflect off of the boundary back into the water. Total internal reflection is all of the light reflects back into the water. And it's called internal because the light is reflecting inside of the water. By the way, this can only happen if the light is going to be going from one medium and attempting to enter into a less dense medium. You cannot get total internal reflection happening when you shine light from air into water. It's got to be from water into air. Mathematically, what's going to happen when you're solving these problems is you will know that total internal reflection happens whenever you try to take the inverse sine of a number that's bigger than 1. And finally, the largest possible angle that will still allow refraction to occur is something which we call the critical angle. Now I want to explain to you what the critical angle is, and then I will show you a demonstration. If the angle of incidence is smaller than the critical angle, then you will have refraction occurring. However, if the angle of incidence is greater than the critical angle, then you will get total internal reflection occurring, like we do at 55 degrees. So 55 degrees is bigger than the critical angle, and you get total internal reflection occurring. You should note that even at small angles of incidence, you do get some reflection of light, but most of the light refracts. At large angles, in other words that are bigger than the critical angle, you get zero light refracting. All right, what we're looking at here is called a refraction tank. It's just a circular dish that can hold water, and the water level is filled up to the halfway point. So where I am indicating with my pen is the level at the top of the water. In other words, my pen is the boundary or interface between the water, which is below, and the air, which is above. The normal line is the line that's perpendicular to the surface of the water. So my pen right now is where the normal line is. Of course, the angle of incidence, because the light is going from the bottom up through the water and into the air, the angle of incidence is the angle between the incident beam of light and the normal line, and the angle of refraction is between the refracted beam of light and the normal line. And as you can see, the angle of refraction here is greater than the angle of incidence. I can measure the angle of incidence by looking at the markings at the bottom, and I would say the angle of incidence right now is about 32 degrees, whereas the angle of refraction is about 45 degrees. Now, in our handout, we started off with an angle of incidence of 15 degrees. And I don't know what we got in the video, but when I'm at 15 degrees here, the angle of refraction is pretty close to 20 degrees. Keep in mind the numbers I'm giving you are being read off of a piece of plastic that has increments of 5 degrees, so I can't read this very well. We then went to 25 degrees, and when I go to an angle of incidence of 25 degrees, I am looking here at approximately 34 degrees for an angle of refraction. Then we went to 35 degrees. Now at this point in time, I want to draw your attention to something. You should be able to notice that there is some light reflecting off of the surface, right where my pen is indicated. And that's reflection that's always going to happen. Even if I went back to 15 or 25 degrees, if you looked closely and if I dimmed the lights totally, we would be able to see some reflection. Anyway, at an angle of incidence of 35 degrees, I'm hitting almost 50 degrees for an angle of refraction. And I'm kind of curious to see how these numbers are going to match up against the numbers that we actually got in the video. When I go to 45 degrees, you should be able to make out that there is a lot more light reflecting. And now I'm at, I want to say it's 70 degrees here. I guess maybe 69 degrees. Somewhere between 69 and 70 degrees is the angle of refraction when the angle of incidence is 45. Now we went to 55 degrees. So when I crank this up to 55 degrees, you can see that none of the light leaves the water. The light reflects 100% inside the water. So that's why we call it total, because it's 100%. Internal, because it's inside. Reflection, because it's reflection. If I were to try to find a critical angle here, it becomes quite difficult. It's maybe hard for you to see, but I can see a little bit of red light right about here. So I haven't quite hit 90 degrees yet. I'm still getting some refraction. If I were to guess, though, I would say that at this point, I've got total internal reflection. And looking at the numbers here, it's looking right around 49 or 50 degrees as being kind of a critical angle. That if I go past that, no question about it, I get total internal reflection. If I go less than that, no question about it, I get refraction. So the critical angle here appears to be maybe 49 or 50 degrees. All right, so I hope that video gives you an idea of what it is we're talking about here with total internal reflection. Let's take a look now at example C. What is the critical angle for light in water? Now what this question is asking everybody is, we already know that 45 degrees for an angle of incidence, if you look at the top of your paper, 45 degrees for an angle of incidence gives us an angle of refraction. And it happens to be, I believe it was 70 degrees. I suppose what we could do is see if 46 degrees works, and if 47 works, and 48 works, and work our way up and try to get the biggest possible angle so that we can figure out what the critical angle is. But there's a different approach. If, when the angle of incidence is smaller than the critical angle, refraction occurs, and if, when the angle of incidence is bigger than the critical angle, refraction doesn't occur, that means it's reasonable to say that when theta 1, which is the angle of incidence, is equal to the critical angle, we get a refraction angle of 90 degrees. This middle case where theta 2 is 90 degrees is not refracting into the air, and it's not reflecting internally back into the water. And that means that in order for us to find a critical angle, this is absolutely important, a critical angle is theta 1 if theta 2 is 90 degrees. You need to know this piece of information. So if we write out Snell's law here, we have N2, which is the air, over N1, which is the water, equals sine of theta 1 over sine of theta 2. So let's put in the numbers. N2 is 1.00 over N1, which is 1.33, equals sine of theta 1, but theta 1 is the critical angle, over sine of theta 2, well, theta 2 is 90 degrees. The angle of refraction that gives us the critical angle is 90 degrees. Those of you in Math 30-1 should know that sine of 90 degrees is 1. So we end up with 1.00 over 1.33 equals sine of the critical angle over 1. Well, we get sine of the critical angle equals 1 over 1.33. So if we find the critical angle now, we do so by just taking the inverse sine of 1 divided by 1.33. And you get 48.75 degrees. Now we're going to have to round that, but I don't want to round it just yet. I want to explain something to you. What this means is if you go back to your table up here in the warm-up, and you put in a number for theta 1 that's smaller than 48.75346663, you will be able to calculate a theta 2. So if you were to do the calculation with 48.75346662, you would get a theta 2. But if you tried to do the calculation with an angle bigger than this, like 48.75346664, you would get an error. So the critical angle is this number, and it's probably got an infinite number of decimals. What we would want to do, though, is round our answer to actually have an answer here. And I don't think we want to quibble about whether we're rounding up or down here. If the question ever said we wanted to round to the nearest tenth, you would say that the critical angle is 48.8. And again, I don't want to get into the fact that 48.8 is actually bigger than the critical angle. We're rounding based on what it might say in an exam question or in an assignment question. All right, let's take a look at another question. What's the critical angle for light in glass? Well, we would always assume, unless it says otherwise, that the second medium is air. So we are talking here about glass to air. We're talking about N1 equals 1.65 to N2 equals 1.00. So again, we start off with Snell's law, sine of theta 1 over sine of theta 2 equals N2 over N1. Theta 1 is the critical angle. Theta 2 is 90 degrees. N2 is air. And what some of you might have discovered here is that we could have a formula that simply says sine of a critical angle is always N2 over N1. And it's okay to memorize that. I don't have a problem with that. So if we take 1 divided by 1.65 and take the inverse sine of that, we would have our answer. The critical angle for light in glass is equal to 37.3 degrees. Take a look at one more. Find the critical angle for light traveling from diamond to ethanol. I feel as though I should point something out to you. I shouldn't have to tell you that it's going from diamond to ethanol. I should be able to just say, what's the critical angle for light at an ethanol-diamond interface? Because you know that the idea of a critical angle is connected to total internal reflection, and you know that for total internal reflection, the second medium must be less dense. That tells you that this is N1 and the ethanol is N2. You should be able to figure that out. Regardless, we take Snell's law, sine of theta 1, which is the critical angle, over sine of theta 2, which is 90 degrees, equals N2, 1.36, over N1, 2.42. So essentially take 1.36 divided by 2.42, then take the inverse sine of it. Again, sine of 90 degrees is equal to 1, so we don't need to really worry about that. 1.36 divided by 2.42 gives me that number. That, of course, is the sine of the critical angle, so I need to take the inverse sine of it, and I get a critical angle of 34.2 degrees. And that's essentially it. Very short lesson. So complete 1 to 6 below. The rest of the problems are optional. Not all of them are difficult. Some of them are just plain refraction problems. Some are refraction and total internal reflection. You can work on them if you like, but do 1 to 6 first. And if you have any questions at all, remember that tomorrow we have a Google Meet during period 1. Show up and I'll be happy to help you then. In the meantime, I hope that that lesson made sense to you, and I hope that you have a wonderful day. We'll talk to you guys later.